Welcome back. Today we'll look at polynomial functions of higher degree. So polynomial functions are written in descending order of degree. We always want the first term to be the highest degree. So we say that a sub n will be the leading coefficient. It will be the number in front of that variable. Remember, if there is no number, we can assume that number is 1. So the highest degree will determine the leading term. And n is that exponent for x, and that determines the degree of the whole polynomial. When we look at graphs of polynomials, there's some basic features. The first is they are continuous, almost like a roller coaster. They're going to be smooth, have rounded turns. They won't have breaks, holes, gaps, or jagged ends. And the domain of polynomial functions is all real numbers. Or in interval notation, we would write negative infinity to infinity. Let's look at these graphs below and determine which of these graphs represent polynomial functions. Well, this first graph, and it can be assumed, even though it's not written, I'll make sure that I write that these have arrows. And we'll just do that for all of them just to make sure it's clear. Okay, so the first graph definitely is continuous. There's no holes, there's no gaps. It has smooth rounded terms, so it will definitely be a polynomial function. The second one has a gap over there, okay? So it has a drop, so we will not say that is a polynomial function. The third one as well has rounded edges, right? Rounded turns, is continuous, goes all the way to the left. It's pretty steep, but it's still a polynomial function. Versus the absolute value function over here for the last one has that corner or that jagged edge, so it will not be a polynomial function. When we look at polynomial functions, we can decide and figure out how they're going to start and end. And we call that the end behavior. So what it looks like to the left and what it looks like to the right. So does it rise or fall? We're looking at the manner in which it ends. So when we look at a function when it's odd, so say the degree is 3, it's cubic, or 5, or 7, right? It's going to have one end pointing up, one and the other end pointing down. So when n is positive, so when the coefficient, the leading coefficient is greater than 0, as x approaches infinity, the y is going to also approach infinity. And as x approaches negative infinity, the y is going to approach negative infinity. So we go towards the negative direction in the left and towards the positive direction in the right. Now, if a, or a sub n, the leading coefficient, is less than 0, as x approaches negative infinity, f of x will approach infinity. So that left behavior will be going up. Versus as x approaches infinity, f of x will approach negative infinity. So that right behavior will be down. Now let's look at polynomials with an even degree. So when something is an even degree, maybe like a quadratic, or something to the 4th power or the 8th power, both hands, both end behavior, will follow in the same direction. When it's positive, as x approaches infinity and as x approaches negative infinity, it will approach positive infinity. F of x is approaching positive infinity for both. When a is less than 0, so maybe a -2, -5, the ends are going downwards. Remember that parabola would have a maximum. So as x approaches infinity and as x approaches negative infinity, both f of x on the left and right will approach negative infinity. So in summary, if we want to make sure we have it this straight, if n is even, and we're talking about something like a quadratic, okay? So when a is greater than 0, that means that the leading coefficient is positive. And it'll look like this, right? So when x approaches, sorry, I have a hard time writing on this. As x approaches infinity, and as x approaches negative infinity, f of x will be going towards infinity. When this is negative, and you have a maximum, as x approaches infinity, and as x approaches negative infinity, f of x will be approaching negative infinity. Now let's summarize when it's odd. So such as like a cubic. So if we have the leading coefficient is positive, it will generally have an increasing pattern. So we're going to have two different things. F of x will approach negative infinity as x approaches negative infinity. They'll pretty much match, right? And f of x will approach positive infinity as x approaches infinity. Now, if something is negative, the overall picture of a cubic or odd degree would be decreasing. So as x approaches negative infinity, f of x is going towards positive infinity. So it's almost considered like the opposite. So if f of x is approaching negative infinity, it's going down to the right, and that's as x approaches infinity. Now let's look at the graphs of these equations. They're a little tricky because not all of them are written in descending order of degree. So we have to make sure you find the leading coefficient. So in the first one, the leading coefficient should be negative 4x to the 6th. And so I'm just going to rewrite this in descending order. So negative 4x to the 6th minus 3x squared plus 1. Now it's clear to see that the front runner would be negative 4. It's an even degree, so we know that both the left-hand behavior and the right-hand behavior will act the same. So even without a picture, we know that it's going to be opening downwards in general. So we could say as x approaches negative infinity, f of x is approaching negative infinity. And as x approaches positive infinity, f of x also approaches negative infinity. It's opening downward. Now let's look at the next one. Here we have negative x to the 5th. This is written in descending order. So our leading coefficient is negative 1. And it's an odd degree. So we know that it's going to essentially have like a negative or decreasing pattern. So we could say, as x approaches negative infinity, as we go to the left, f of x is going up in the positive infinity direction. And as x approaches positive infinity, goes to the right, f of x is falling, and it's going to negative infinity. Now for C. For this one, we can see that x to the 8th is our leading term, and 1/3, even though it's a fraction, it's still going to be positive. So if our leading term is positive and our degree is 8, we knew that this is essentially going to be opening upwards. So we can write this out as x approaches negative infinity and goes to the left, then f of x approaches infinity. And as x approaches positive infinity and goes to the right, f of x will also go up towards positive infinity. Now let's go to the next one. Okay, from here, this one is written in descending degree, and you can see that it's 5 x to the 7th. So if we know that the leading coefficient is 5, well, we know in general it's going to have an increasing pattern. So as x approaches negative infinity and goes to the left, I'll put as f of x will be approaching negative infinity. It's going down or falling. And if we go to the right, as x approaches positive infinity, the function will be rising or approaching positive infinity. Now let's look at some vocabulary, because you guys have worked with these a lot already. So when we look at zeros, we can say x equals a is a 0 of f of x. When we set the equation equal to 0, we could say this is a solution. Remember, that's when f of x equals 0. X minus a would be a factor of f of x. And a0, which is an ordered pair, would be an x-intercept. So even though they all mean the same thing, in general, looking at a graph, we can say them a little bit differently based on how they're written. If we want to figure out the number of turning points a graph would have, we would look at the degree and subtract 1, and that would be the most number of turning points. And we also call those relative maxima and minima. In general, looking at multiplicity, we're still looking at zeros. When k, so if we have any of these zeros as factors, when this exponent k, and as long as it's greater than 0, whenever it's odd, the graph will cross the x-axis. When k is even, the graph is going to touch, and I even say bounces off the x-axis. Okay, we're going to look at what that means in just a minute. Okay, so first here we have an example of a polynomial with a degree of 5, and it has these unique zeros. So if we know that we have x is a 0, and we have these two answers, root 3 and negative root 3, well, we only have 3 so far, but we can use the multiplicity rule to add those two other zeros and make this x equals 0 have a multiplicity of 3. So writing that polynomial, well, we can combine these two. I'll put them over here using the sum product, right? When we add those together, we get 0. The product would be negative 3. So if we're going to write that equation for those two, we would write x squared minus the sum, but it's 0, plus the product, which is minus 3. If we were going to include the zeros, right, we could say, well, make an x in front, and 0 would be a 0 as well. So if this is a function, I have to make sure I put f of x on the other side of the equal sign. Now what I was talking about with the multiplicity is that so far we only have 3 x's or 3 zeros, but we want this to have a degree of 5. So what we can do is say, well, the 0 has a multiplicity of 3. And so now this polynomial equation is a 5th degree polynomial equation. Let's look at what graphs would look like. So here we have 3 graphs, and for each of these graphs, we're going to write an equation. So here when x equals -8, remember that's going through the graph. So that means it's going to have a multiplicity that's odd. And then at -4, that's going to touch, or I like to say bounces off the x-axis. So that's going to have a degree that's even. So if I was going to write an equation, I'd have to make sure I write the factors. This would be x plus 8, and this would be x plus 4. Now, we want to make sure that the one at 8 is odd, because it goes through. So I'm just going to put 3. Okay, we're just doing this as an example. We're not, it's this general sketch. And then x plus 4, remember that has to be even, because it bounces off the graph. So I'll just make that 2. So this is a possible equation for this sketch. We'd have to actually plug it in and find, let me just write this here. We just have to find that A to figure out exactly what that equation was. But it's definitely going to have those zeros. So if you wrote a possible answer in factored form like that, that would be good for the sketch. Now let's go to the next one. For this one, we have quite a few zeros. We have -7, that goes through, right? That's going to be odd. We have -5, which is going to be also odd. We have 1, which is going to be even, the only even in here. And then we have 5. So if we're going to write this equation, it'll be f of x, and I could just write x plus 5. Remember, that's to the 1 power, so that is odd. X plus 3, that's also odd. X minus 1, make sure I square that because it's even. And then I'll add one more at the 5, x plus 5. Now you could add more degrees, but this will be good for a sketch. Let's go over here for the next one. So you can see from this graph, all of these bounce off the axis. So all of these are going to have to be even. So the first one is x plus 6, and I'm just going to make sure they're all even, so I'll square them. X plus 1 squared, x minus 3 right here, and then x minus 9 squared. And that could be an equation, possible equation for that graph. Now let's sketch some of these graphs. When we sketch the graphs, we want to first consider the leading coefficient test. We're going to decide what's going to be the end behavior for these graphs. And then we're going to find the intercepts, so the x and the y intercept. We're going to look at the multiplicity, and that's easily determined when you factor the equation. We're going to consider the turning points. So remember, the turning points, or the maximum number of turning points, is n minus 1. And then we could test the intervals on both sides to verify. But again, I want to make sure and re-emphasize that these are sketches. Okay? So for this one, when I look at this graph, or this equation, we have 2x cubed. So we know that this is going to, in general, have an increasing behavior. And as x approaches negative infinity, the function is going to be falling. And as x approaches positive infinity, the function is going to be rising. Now let's look at the equation a little bit more carefully. So from here, we can factor this pretty easily with the GCF. So I'm going to factor it. So it's 2x squared, and then we get x minus 3. Well, now it's a little bit easier to see those x-intercepts. We definitely have an x-intercept, or 0, at 0, and another one at 3. When I look at the degree, we can tell that this will have a multiplicity of 2. And the 3 will have a multiplicity of 1. When I want to find the intercepts, we know that we already have the x and y intercept when x equals 0. So let me sketch this. So at x equals 0, that's going to be 1 point in the graph. And at x equals 3, that'll be another 0. So this graph is going to bounce off the 0. Remember, it's starting to the left. It's going to bounce off the 0, and then it's going to go through the 3. Let's look at the next one. For this one, we can also tell that it's going to have x to the 4th as the highest degree. And that leading coefficient is negative. So if the leading coefficient is negative, we know that it's going to be opening downwards in general. So as x approaches negative infinity, it's going to be falling. And the same thing on the right side. As x approaches positive infinity, f of x will also be going down or falling. Okay, so if I want to find the zeros, it's probably a little bit easier just to factor it. And since I have a lot of fractions in here, if I factor out negative 1/4 x squared and get rid of some of these fractions, I'll get x squared minus 6x plus 9. And that can factor into, because it's a perfect square trinomial, into x minus 3 quantity squared. Now we have two zeros here. We have a 0 at 0, and we have a 0 at 3. This time, though, it's going to bounce off of the 2, or bounce off of the 0, because it has a multiplicity of 2, and it's going to bounce off the 3. So I'm going to make sure I put the 0 here, and I'm going to mark this as 3. So this graph, remember, is going to dropping to the left, bouncing off of the 0, bouncing off of the 3, and going back down and falling when x approaches positive infinity. Now for the last concept. And this is a really, really important concept. The intermediate value theorem, also known as IVT, is something that you're going to come across a lot in calculus. So the IVT is pretty simple in its idea. So if we have a value, a closed interval here, between a and b, and we have a continuous function that goes through a and b, and we want to make sure that f of a does not equal f of b, well, then we know that there's going to be one value here in c that's going to equal d. Okay, so we know that somewhere in there that it will cross that path. So whenever you have perhaps a street or a railroad or something, if you have your house is over here and your friend's house is across the tracks, you know that eventually, if you're going to go to your friend's house or your friend's going to come to your house, one of you will have to cross over the tracks. That same idea It doesn't matter if you go around here or around here, you're still going to have to cross the tracks. That same idea is important when we look at zeros. So if we want to find or approximate real zeros, we'd have to figure out when is the y value negative, and then when is the y value positive. And somewhere in between will be your zero. So for this one, we're using our tables to approximate the real zeros. So we could start by plugging some values, -2, -1, 0, 1. And you can see right here, they start to be pretty close, right? So somewhere between those two values, we know that right here, somewhere between those two values, because there's a change in the y from negative to positive, there's going to be a 0. So you can plug that into your table here. You can see the values, and you can adjust those increments to get even more values. And what you can start to see is it's negative right here, and then it starts to become positive. So when the function, when you plug in -0.8, you get -0.152. When you plug in -0.7, you get positive 0.167. So since there's a sign change there, the 0 must exist between -0.8 and 0.7.